Right, so we're covering arc length and curvature on this lesson, and we just got a few definitions. dr is a displacement differential, and it's just r prime of t dt. ds is an arc length differential, which is just the length of dr. So that's the magnitude of r prime of t dt. And then s for arc length is the sum of the arc length differentials over the curve, which is the integral from a to b of the magnitude of r prime of t dt. So we're going to compute arc length for this vector function, where t goes from 1 to 4. So first we need the derivative. So let's begin. R prime of t is 1 over t, 2t, like that. And then we'll need the magnitude of that. You can think of this as distance equals rate times time. For the arc length, the rate is the magnitude of the velocity vector, which is the speed. You're just doing speed times time and adding that up to get the distance, which is arc length. Okay, so this is a velocity vector. The speed is the magnitude of the velocity vector. So I'll just go and write velocity here so that you see it. Okay, speed is the magnitude of velocity. Okay, so this would be the square root of 1 over t squared plus 2 squared plus 2t squared, like that. So that's sort of obvious what that'll be, but let's see here. So I think it's going to be 1 over t squared plus 4 plus 4t squared, like that. And I wouldn't have done this problem if you couldn't integrate it. So that thing's got a factor. Okay, I just know it factors. So it factors this way: 1 over t plus what? Yeah,
plus 2. Plus 2.
Now, do you get? Does that look right? Plus 2t?
Yeah.
20 squared, like that. So if you multiply the in and the out, you get, if you multiply the inside and the outside, you get the 1 over t times 2t, which is 2. And then, of course, you have to double that. So you get the 4. And yeah, so that's right. And then here, we would normally say this is the absolute value of 1 over t plus 2t. But we might note that this is positive since t is between 1 and 4. So we can drop the absolute values. Okay, nothing in there could be negative. So, so that means we can just say, oh, well, then this is just 1 over t plus 2t. Okay, and then the arc length s is the integral from 1 to 4 of the magnitude of r prime of t dt. So this is the integral from 1 to 4, and it turns out to just be 1 over t plus 2t. dt. All right, any questions? So this is just going to be natural log of t from 1 to 4 plus t squared from 1 to 4. Okay, and so what do you get there? Log 4 minus log 1 plus 4 squared minus 1 squared, right? So log 1 is 0. So what do you get there? 16, so log 4 plus 15. Okay, any questions about that? And these are very carefully chosen problems. I always like problems that have 3 components in them, that after you take the derivative and the magnitude, that it comes out as a perfect square. So, so that it ends up being actually a super nice integral. And you can expect problems like this, just like this on your exam.
Professor, quick question. So, basically, if we get something like this, you take the derivative of um, RT and then find the magnitude and then plug it into the equation, the formula.
Yeah, into the integral. Yeah, that's right. I mean, we're just, this is the arc length formula here.
Yeah. Okay. Perfect. Thank you.
Okay, no problem. So that's just one little piece of this. Arc length is, the lesson is called arc length and curvature, right? So we've got arc length down, but curvature is more complicated. Now you can see, as I said, you're just doing distance equals rate times time. The speed here is the rate, and dt is the time. And you just add that up over the curve, and you're getting, distance is the arc length. Okay, so that's actually pretty straightforward, not a surprising result. But what we need next is something called curvature. And curvature takes a little more work. Curvature is a geometric property. So we need to find a way of describing these curves in terms of its geometric properties that don't involve any physics. And the problem with what we've got set up right now is it all depends on time. And we don't want it to depend on time, because arc length should be a geometric, sorry, not arc length, but curvature and arc length. Both of these should be geometric measures. So we're going to try and come up with a measure that describes something about curvature on a curve. So I want to go ahead and define something called the arc length function. This is something that gives the relationship between arc length and time. It's just the arc length formula. Arc length is S, and time, which is T. And if you know the relationship between arc length and time, and obviously there's a relationship between arc length and time. I mean, if you're driving 50 miles an hour for 3 hours, then distance is rate times time, right? It's just a distance equals rate times time kind of thing. But what we want to do is, once we know the relationship between between distance or arc length and time, you can change your time parameter to an arc length parameter in the space curve. And that allows us to say, okay, well, now if we're describing position in terms of arc length instead of time, then any measurement we do is now going to be a geometric measure, not a physics thing where you're looking at rates and stuff like that. So let me just kind of define the arc length function. Let's say the arc length function gives this, it is the relationship. So I'm actually repeating what I just wrote. I'm ashamed. Okay, here's the relationship. S, not just S, but S is going to be a function of time now. Okay. And I'm going to say, instead of integrating from A to B, we're going to integrate from A to T. And then you're going to just do rate times time. But the rate, we have to use a dummy variable because T is in the upper limit here. So we can't use T. We use a Greek T, which is a tau. Okay, so I'll just say that's just the arc length formula. But the idea is you're kind of moving along a curve. So this point right here is like R of t. Okay, down at the beginning is R of A. And S of t would be like the distance traveled at time t. Okay, so it's something that grows as time increases. You keep moving and you keep covering more distance. Okay. And then you might want to notice that the fundamental theorem of calculus tells us that if you do ds over dt, that's just the magnitude of r prime of t. So we'll need that because ds over dt comes up in a lot of the discussions. Okay, so a little example here. We had this function, we just reused the one we did a second ago. So r of t was the vector function log t 2t and t squared. And then I think that the r prime of t is 1 over t to 2t. And then the magnitude of r prime of t is, well, it was it 1 over t plus 2t? That's what we did before. And so s of t is the integral from, I think we went from 1 to 4, so we'll go 1 to t here, of the magnitude of r prime of tau d tau. Okay. So here, that would be the integral from 1 to t, and then we would just put in a 1 over tau instead of 1 over t plus 2 tau. And of course, this is the integral we did just a second ago, d tau. Okay. And so here we'll say that's the natural log of tau from 1 to t plus tau squared from 1 to t, like that. And so the tau, we just call that a dummy variable. It's just holding a spot until you put the t in for tau. Okay, we don't like it when you substitute a variable into itself. So we have to use a dummy variable. Okay, but now you can do that substitution. So you get natural log t minus natural log 1, which is 0, and then plus t squared minus 1. Okay, so this is our arc length function. S of t is log t plus t squared minus 1. So this gives distance at time t. Okay. So any questions to this point? So as time increases, the distance increases as well. And I did not use the absolute value on the logarithm because everything's positive. I guess I should have, I probably should have put absolute values around that. So I apologize. Okay, but again, t is positive, so it's not really necessary. Okay. Now, so this is, the idea here is basically, so if we want to parameterize by arc length, first thing you have to do is find S of t. Let's say S, which is S of t. Okay, second thing, you would have to solve this equation for t. Then, so t, which would be like the t of S. Yeah. Okay, so replace t in R of t. With the t of S. Okay, call the result R of S. Okay, so R of S will trace out the same curve. But the input is arc length. So the input is arc length, and the output is position after traveling that length. Okay, so you're inputting an arc length and it's outputting a position, and there's no time. So there's really, that kind of removes all of the considerations. If there's time, then you think about velocity and acceleration. And that removes all of those considerations. I guess I could do a quick example of that. So let's just see if I can do it very quickly. So something similar. By the way, this one here that we just did, I can't solve this for t. So I'll use this example more, but it's not a good one for demonstrating what I just described. Okay, if I want to demonstrate that, I need a different example, and it'll have to be a lot easier. Okay, the only one I give this step-by-step process, but you actually can't do it unless the function is super easy. Okay, so let me do one that's super easy. So real quick example. Oops, I think I just did something I didn't mean to do. Okay, so a real quick example. So here my R of t is going to be 2 cos t, 2 sine t, and t over 4. Anybody know what shape that is? What shape is that?
A helix?
Yeah, that's a helix. Thank you. And so r prime of t is going to have a -2 sine t, 2 cos t, and then just 1/4, like that. Magnitude of r prime of t here, super easy. So you're going to get 4 sine square t plus 4 cos square t plus 1/16, right? So so that'll just be the square root of 4 plus 1/16. Which is square root of 17/16, I think. Which is the square root of 17 just divided by 4. I think I made a mistake. That's funny. I was doing 1 and a 16th. So let me fix this. So 4 times 16 is 64. So I think this would be the square root of 65/16 is what I should have said, which is the square root of 65 on top over 4. Sorry about the mistake. Okay, any questions? Okay, so yeah, and then your S of t, I'll just say S, which is S of t, would be the integral from 0 to t, because see, t starts at 0 here, so that's my lower limit. So 0 to t of the magnitude of r prime of tau d tau. Good news is that's super easy. We just have the integral from 0 to t of the square root of 65/4 d tau. So this is square root of 65/4 tau from 0 to t. So this is the square root of 65/4 times t. That's just distance equals rate times time, because the rate was the square root of 65/4. That's the magnitude of r prime. That's the speed. And t is the time, and s is the distance. So distance equals rate times time. No kidding. Okay, but then the instruction said to solve for t. So if we solve for t, then that means t is 4 over the square root of 65 times s. And I am not going to clean that up. I apologize. And then when we say r of s, we're just putting in instead of writing t, we'll put in 4 over the square root of 65s. So here we go. So we're going to write 2 cos of 4 over root 65 times s, comma, 2 sine, same thing, 4 over root 65 s, comma, need some more space, so I'll deal with that. And then what, I have to do t over 4. So I think I'm going to get a square root of 60. Is the square root of 65 over 16 times S? Oh no, I screwed up. I'm looking at the wrong one. T over 4. So is it 1?
16 over the square root of 65.
But it's over 4. Don't the 4s cancel? Am I crazy?
That's what I was thinking, that they would cancel.
Yeah, they do. And I just lost my mind temporarily. It wouldn't be the first time. Okay, and so so on this curve, at
Yeah.
At S equals 1, distance traveled is 1. Oops. So that occurs when you're at R of 1. It's an arc length parameter. It's the same curve. It's still a helix. Okay, but you've basically slowed it down. If you think about it, when the parameter is 1, it's sort of like you're going 1 mile an hour, so that if you go for 1 hour, you've gone for 1 mile, right? So the time is the distance is sort of the idea. Okay, but the idea is that the real idea is that we've taken time out of it, which is what we want for what we're about to do next. Okay, so that's switching to an arc length parameter. Okay, so did I say that yet? Okay, so this process allows us, well, let's say means R is parameterized by S, which is called the arc length parameter. So I just wanted you to hear that term. Okay. Any questions? So we got that. Okay, so the next thing, this is going to be the unit tangent vector. Okay, unit tangent vector is going to be called T of t. Notice I'm describing that in time, not through arc length. Okay, well, since r prime of t is a tangent vector, how do we get the unit tangent? Let's just say it is a tangent for all t. What's T of t? Oh, by the way, this should have a hat, not a barb. So when I say T of t, I mean there should be a hat on it. So what's the formula for T of t? How do you make it a unit vector?
It would be T barb over the magnitude.
Magnitude.
Yeah, we want to do r prime, so that r prime gives the direction, but its length is wrong, right? So we have to divide by the magnitude of r prime. Any questions about that? So, so for the example, and the unit tangent is going to be instrumental in determining what curvature is. Okay, so so when R was this first one I did, R of t, I should say, which was log t, I think it was 2t and then t square. R prime of t was 1 over t to 2t, and the magnitude of R prime was it 2t plus, is it 1 over t plus 2t? Okay. Okay, and so when we do t of t, we put a hat on, get it all dressed up. So we do R prime of t, of the magnitude of R prime of t. Like that. Okay, and so R prime, so that's going to be 1 over t 2t over 1 over t plus 2t. This is an improper fraction. I don't like those. No, that's not an improper fraction. That's a what do they call this? Complex fraction? I haven't taught algebra in so long. This is a complex fraction, which is bad. So we're going to multiply the top and the bottom. I think we should just multiply by t, right? So let's multiply by t. And that'll look better. So we'll just have 1, 2t, and 2t square on top. And then maybe I'll write 2t squared plus 1 like that. And I'm okay leaving it like that, but maybe just so that I can say I did, I'll be really good and expand this. I'm not a big fan of expanding these. I liked the previous because it takes less to write. So this is a unit vector for all t, unit tangent. Okay, so I kind of think of my curve like this, and then all these unit tangent vectors, all with exactly the same length. But at different times. Yeah, put this there. So I'm trying to make these all look like the same length, but I'm sure that that'll fail somewhat here. So every one of those is a unit tangent and it moves in time. Okay, any questions? Any questions? Okay, well, we want to measure curvature by how fast t changes. So I want you to note T never changes in length. Only direction. Okay, so T prime let's say of T measures how fast T changes in direction. But this depends on the speed of motion, which we don't want. Because this is parameterized by time. And we don't want this, okay? Okay, we want to measure change in direction geometrically. Okay, so T prime of S measures change in direction and is not affected by speed. So measures the change of, I should say rate of change. Of the direction of T independent of speed. Okay. Curvature needs to be a scalar, so we'll use magnitude of T prime of S. Okay, so here's our definition. So kappa is curvature. Okay, and it's just the magnitude of T prime of S. Okay, which is an absolutely unworkable formula. So this is, I just say this is a non-computational formula. Because you can't compute stuff with this. Okay. So the theorem is pretty straightforward. Well, before we write the theorem down, let's just do this as scratch work so that I don't have to do a proof. So note that dt over ds, obviously we're going to do a chain rule on this and just say, well, that's that's going to be dt capital T over d little t times dt over ds. And I don't really want to do dt over ds because that would mean I'd have to find the arc length function and solve for t, which you can do, but it's super hard. So it would be better to do d big T over d little t, and then divide that by ds over dt. Just remembering what I had said before, that ds over dt is just speed. So this is the magnitude of r prime. And we had that came up when I was talking about the fundamental theorem of calculus a little bit ago. So this is a computational formula here that curvature kappa is equal to the magnitude. Remember, we have to take the magnitude of this. So you'll do the magnitude of t prime of t over the absolute, or no, another magnitude of r prime of t. So that's just an application of the chain rule right there. Alexa, turn on the bedroom lights. It's getting dark in here. Okay, so any questions? So I have to do an example. This is sort of a headache, I know, but good news is we've already done most of the work here. So let's get back to that last one, and I'll just go ahead and refresh here. So our r of t was natural log t. I think it's 2t and then t squared, right? Our t of t we've already done, and I think it was, you guys correct me if I'm wrong here. I guess I could just copy it down. That guy. Why would I write that mess again? Okay, so I'm just going to copy and paste that down. There. I need the magnitude of r prime of t. So the magnitude of r prime of t, I think we had wasn't it like was it log t plus 1 over t? I can't remember. No, it was 1 over t plus 2t, right?
Yeah.
Thank you. I just can't remember. There it is. And let's combine these so that we make this a 2t squared plus 1 over t. I think that's better for what we're about to do. Okay, so, and another thing I want to do is I'm going to do a quotient rule here. I'm going to write my t again as I originally had it, 1 comma 2t comma 2t squared, like that, over just a single denominator. It's easier to work with like this because we can use sort of a vector form of the quotient rule if you're dividing by a scalar function. where you do the derivative of the top times the bottom and so on. So that's what I'm about to do. I'm going to do d over dt of t. Okay. And so just a real quick notation. I just want you to notice that I'm going to write this as t prime with a barb on it. The thing is that once you take its derivative, you can't control how fast it changes. It may be a unit vector, but it can change really fast. So just because it's a unit vector doesn't mean its derivative will be a unit vector anymore. So it loses its hat and it takes a barb, I guess. I mean, I don't know what else to do notationally here. So point is, I'm going to do a quotient rule. So I'm going to do the derivative of the top, which is going to be 0, 2, and then 4t times the bottom, which is 2t squared plus 1. And then I'm going to do minus the top, 1, 2t squared times the derivative of the bottom, which is just 4t, okay, over the bottom squared. So what you're really doing is 3 chain rules at once. I mean, they all have the same denominator, so they're all going to have the same chain rule. We'll just do over 2t squared plus 1 squared. Okay. And I think I don't know. In my mind, it's better to do it this way. I don't know if it is, but less writing for sure. Okay, so let's see if we can combine some of this stuff. So what I'm seeing is a 0, a 4t squared plus 2, and a 8t squared plus 4t. Okay, and then minus, I get a 4t, 8t squared. And then we get a 8t to the third. Looks horrible.
Professor?
Did I make a mistake?
No, is it okay if you just show me how you kept track of all of that? Like
You mean on this bit right here?
for the step that you just did for the numerator?
Oh, all I'm doing is the scalar multiplication. So now look, I'm not sure. I'm not saying I didn't make a mistake, but all I did was multiply this 2t squared plus 1 through this vector here. That's just a scalar multiplication.
Oh, I see. Oh, okay. That's
And
better.
now I'm doing it again on the second vector.
Okay, that makes more sense.
Yeah,
Thank
no
you.
problem. No problem. Thanks for asking.
Professor,
Yeah.
is that the 8t squared should be 8t to the cube?
Agreed. Thank you. So you are talking about, that's what you wanted, right?
Yes.
Thank you. Keeping me honest. I do appreciate your help, everybody. Okay, so now I'm going to do 0 minus 4t. So that's going to be negative 4t. 4t squared plus 2 minus 8t squared. So I think, what if I wrote it as 2 minus 4t squared, comma, and then we've got an 8 to the third, 8t to the third plus 4t minus 8t to the third. I think that's just 4t, like that. And then this is over 2t squared plus 1 squared. Okay, now that's one thing. You want to factor that if you can, because you see the next thing is, I don't know if you notice, but up here we have to take the magnitude of this. I think my screen's frozen. Hang on, I'm going to pop out. Yeah, screen is frozen. Let's see if I can pop back in. There we go. Still super choppy. Okay, what I had said was I just circled this thing. We have to take the magnitude of this t prime of t. Okay, so let's see if I can get this to work. It's going really slow. Might be time for a break pretty soon. Okay, so I want to make this vector as simple as possible always before I start taking its magnitude. There's not much you can do, but I am going to take out a -2, I guess. So I'm going to write this last bit as a -2 times a vector. So inside I'll have a 2t and a 2t square plus 1, I think, or -1. 2t square minus 1. Yeah. And then a -2t. And I think it's just good to practice this anyway. Don't forget, you're going to do this over 2t squared plus 1 squared, so that when we do the magnitude of t prime, I'm going to take the absolute value of the scalar. So that you're going to take the absolute value of -2 over this 2t squared plus 1 squared. Now, if that 2t squared plus 1 squared was distributed through the vector, I hope you can see how much harder this would be. It's hard as it is, okay, because I still have to do the square root, but you want to factor as much out of there as you can. All right, so I got this 2t, it's squared. I've got the 2t squared plus, sorry, -1. That's squared. And I've got another -2t here squared. So I think this is going to come out pretty nice. Here, I'll just write 2 over 2t squared plus 1 squared. And the square root, if everything goes right, it'll be sort of magical. Ready? 4t squared plus, there's going to be a 4t to the 4th, right? Minus 4t squared plus 1 plus 4t squared. Not a 4t squares in there. And obviously you can cancel some of it, like that part. And then let's write it in descending powers. So you get 2 over 2t squared plus 1 square root of 4t to the 4th plus 4t squared plus 1, right? Which is a perfect square inside. Like that. Technically, there's an absolute value when you take the square root of a square. So technically, you have this times the absolute value of 2t squared plus 1, like that. But this is positive, so we're not going to fuss about that. And we'll just say this is, so you don't need the absolute value, so you can just say 2 over 2t squared plus 1. That's the curvature. Should be always positive. Curvature could never be negative. Okay. And I want to just take a pause. You know what, you guys, I think we've been going at this for some time now, and I think I want to give you a break. So let's do a break till about 7:25. And we'll pick this up. We're not done with this lesson, but we're getting pretty close. Okay, so I'll see you guys in a few minutes.
See you later.
Okay, so I am worried that that was not the curvature. Okay, so unfortunately, I'll have to edit this out. All we did here was the magnitude of t prime. So let's delete that statement. Okay, and remember that curvature is not the magnitude of t prime. It's basically looking at how fast that unit tangent changes direction, but it has to be independent of speed. So you basically have to divide the speed out. Just to remind you that we defined curvature at kappa to be the magnitude of t prime, which we just did, but then you have to divide by the magnitude of r prime. Okay, divide the speed out so that it becomes a geometric property is the idea. So we just have this last result, the 2 over t squared plus 1 here. Let's just copy that down. Okay, and maybe divide out the speed, which we did previously. So let me see if I can find that. This one is the speed. Okay, so I'll copy that down. Like that. So I think we're going to get a square down there. So we're going to get a 2t over 2t squared plus 1 square. So I apologize, I jumped the gun on the curvature. That's it for that example. Unfortunately, I don't know if I need that one right now. I will. Okay, I do need this. Okay, so there's a theorem. I didn't want to prove something I didn't need, so I guess I need it. I know I need it later, so I may as well do it. So the theorem says, this is weird, but it just says if r of t, well, let's just do it this way. If the magnitude of r of t is constant for all t, okay, now that's a position vector. So careful, what we're saying is that you're not in a constant position. We're saying that the magnitude of the position vector is constant. Okay, then if you think about it, the only way you could do that is if you're moving basically on a circle or a sphere. Okay, let me draw that. Snap that in real quick here, right there. Nope. It's right there. Okay, so it doesn't matter where I go on this circle, or let's pretend it's a sphere either way. R of t is not constant, but its magnitude is constant. Okay, it's the magnitude is the radius of the circle, and so what we're just saying is the distance from the origin is a fixed length, and that's just the definition of a circle or a sphere. Now, I'm not saying if you're on a sphere, the curve is not the sphere. It's just that your curve is embedded in the sphere. And what we know about moving on a circle or a sphere is that the tangent vector is going to be perpendicular to the circle, and therefore I should say perpendicular to a radius. So I'll call this r prime of t here. The tangents to circles are always perpendicular to their radii. Okay, so let me just position this a little better. So what the theorem just says that r prime has to be perpendicular to r. So r prime of t is perpendicular to r of t for all t. And again, it assumes that the curve, this is a continuous curve. So it assumes r is smooth. Okay, so Of course, it has to be smooth, but if you're moving on a circle, let's keep going here. The proof is pretty straightforward. Just says to remember that R dotted with R is the magnitude of R squared. So magnitude of R of t equals a constant that's given. Okay, so magnitude of R of t squared would be c squared, no kidding. But then that's just R dot R equals c squared. We take a derivative on both sides. And of course, we'll get 0 on one side, and we'll get R prime dot R plus R dot R prime. That's the product rule for dot products, works just fine. Equals 0 on the right side. Those are the same, so you could view this as 2 R dot R prime equals 0, which of course you can divide by 2, and you'd have R dot R prime equal to 0. What does that tell us? That's our proof, right? So that if the dot product is 0, that means that position vector is perpendicular to
R prime.
Yeah. Thank you. Okay, so that was just kind of a side thing. There's another theorem. So I gotta do this. It's a special formula for curvature that sometimes works out nicely. So it says that kappa, remember that's curvature, can be computed this way: magnitude of R prime cross R double prime over the magnitude of R prime. That's curvature. And that looks, all right, to the third, my bad. The denominator's to the third power. Okay. Okay, sorry about that. So I got to prove this. So first thing is that's it. That's one computational formula for kappa. There's another one that we've already used. Remember, kappa is curvature. Okay, so this is a little bit ugly, but watch how we do this. For the proof, the first thing we want to do is note that the unit tangent is equal to R prime over the magnitude of R prime. Oh, don't want that magnitude on top though. R prime over the magnitude of R prime. Like that. R prime is equal to the magnitude of R prime times the unit tangent. Now, just to remind you, we said previously that the magnitude of r prime is also the derivative of arc length, which is just speed. Okay, so I want to write this as ds over dt times t. And that should be a hat. Yeah. Then next thing I want to do is compute r double prime. So r double prime would be the derivative with respect to time of r prime, which is the derivative with respect to time. And by this way, this statement will be, we'll bring this one back when we talk about acceleration in the next section. So I'm going to do the derivative with respect to time of ds over dt times t here. Okay. And so this is a product, so we need a product rule. So we're gonna do the derivative of the first, that'll be d2s over dt squared times t plus ds over dt times the magnitude, no, times the derivative of t. Now it's gonna lose its hat and get a barb, because I don't think it's going to be a unit vector anymore, or at least I can't prove it will be. Okay. I want to note that t is a unit vector. I'll just say it's constant length. So we just proved in this theorem up here, if we have a constant length, then its derivative is perpendicular to the vector. So here I can say that t prime will be perpendicular to t. Okay. Now I want to show you what r prime cross r double prime. I'm building up this expression for kappa here. Okay, so here we're doing r double prime, sorry, r prime cross r double prime. And so we're going to bring in both of the expressions. The first one for r prime was ds over dt times the unit tangent. And now we're crossing this with d2 r double prime, which is d2s over dt square times the unit tangent plus ds over dt times t prime, which is perpendicular to t. Now, there are no derivatives. The derivatives are done. So this is just distributing, and cross products do have a distributive property. So what I would do next is say, all right, well, this has got a ds over dt times a d2s over dt squared. And then I'm going to, those are the scalars. And then I have a t cross t here. Just distributing the vectors together. And then plus, here I'm going to have a ds over dt times ds over dt. So this is going to have a ds over dt, a quantity squared, and then I'll have a t cross t prime. Like that. Okay, so something is 0. Can anybody tell me what's 0?
Unit vector t cross unit vector t.
Yes. Vector crossed with itself, or any vector crossed with another vector that's parallel to it will give a 0. Now, this is a 0 vector, not a 0 scalar. Okay, so that whole first term vanishes. This is nice. So this is ds over dt squared times t cross t prime. Okay. Now, if you look at the definition for kappa here, it's using the magnitude of r prime cross r double prime. So what I need to do is see what the magnitude of this cross product looks like. And so that's where I'm going next. So we're going to do the magnitude of r prime cross r double prime. Okay. And so here we go. I'm going to take the magnitude. I'll just take the absolute value of ds over dt squared. And of course, that's absolute value of a squared thing is always, you don't need the absolute value. So I'll drop that. And then I'll have times the magnitude of t hat cross t prime, like that. Okay, and then so for the first part, we'll just say ds over dt squared, and that's just speed squared, like that. Now, don't forget for this thing that the magnitude of v cross w, just as a principle, is magnitude of v times the magnitude of w times the sine of the angle that separates them. Okay, so I'm going to use that now. I'm going to write magnitude of t. Oops. Magnitude of t hat times the magnitude of t prime times the sine of the angle that separates them. Now, what's theta?
90, because they're perpendicular.
Right, the theorem, you have to remember that t has constant length, so it's perpendicular to its derivative, okay? So that goes back to this statement here. If the vector has constant length, then its derivative is perpendicular to it. Okay. So I am referring to this statement right up here. Again, and I'm going to draw an arrow down like this. Nope, not that way. We can hear you. Yeah. So right here, theta is 90 degrees. We'll say pi over 2. So sine theta will be 1. What's the magnitude of t prime? That's 1 also, right? So in the end, this is just ds over dt squared times the magnitude of t prime. And you know that t prime is very closely related to curvature. Magnitude of t prime is closely related to curvature. So we can see the relationship between the magnitude of r prime cross r double prime. Somehow it's related to curvature. So it's not surprising that it comes up in the curvature formula. What you need to do next is divide both sides by, maybe we'll write this as, remember, ds over dt, this is the magnitude of r prime. That's square times the magnitude of t prime. My bad. Okay, so here I can say that the magnitude of r prime cross r double prime. Now, all I'm going to do here is divide it by the magnitude of r prime to the third. And say, well, then that's got to be this other thing that we just worked out. Okay. Over the magnitude of r prime to the third. And of course, that's just the magnitude of T prime over the magnitude of R prime. And what's that? That's what they call kappa. That's the curvature. Okay, so that's a proof. We'll just write QED. It is proven. And I guess we can do our problem again. Let's see if this works okay. So back to our example, I think we did do the curvature 2t over 2t squared plus 1 squared or something like that. Let me go ahead and write it down again. R is log t, 2t, t squared. R prime is 1 over t, 2t. And then the first time I'll compute R double prime. Okay, so that's going to be negative 1 over t squared, 0, 2. That's nice. No big deal. Also, while we're at it, let's remind ourselves that the magnitude of R prime, we did it a couple of different ways, but let's write it as this one, 2t squared plus 1 over t, like that. Okay, I have to do, I'm going to compute kappa again, but this time I'm going to do R prime cross R double prime formula. So here we have to do R prime cross R double prime, like this. And here we go. Okay, so that's R prime cross R double prime. Looks ugly. Now I'm going to do this in my head. So currently I'm doing the minor, which is this cross product here, 4 minus 0. I think that's just a 4. Okay. And then minus j hat. And so now the little 2 by 2 determinant I have to do next is on the extremes here. I have to do this one. So I'm going to do a 2 over t minus negative 2 over t squared. See, what did I say? 2 over t minus, there's a double negative. So plus 2t over t squared. And then plus k hat. And on that, I'm doing this one, and it looks like just 0 minus negative 2 over t squared. So it's going to be just 2t squared. Sorry, 2 over t squared. Okay. So I think we can write this now as a vector. It'll be 4. So that's 2 over t plus 2 over t is 4 over t. So we just say 4 over t. And then 2 over t squared, like that. I think I'd factor, we have to take the magnitudes. So as usual, I like to factor these before I take magnitudes. So I recommend you do the same. So let's take a 2 out, and then we'll have a 2 over t, and just a 1 over t squared, like that. Okay, any questions? Have to take magnitude of this. So the magnitude of R prime cross R double prime is going to be the absolute value of 2 times the square root. Mistake? Did I make a mistake?
Yes, don't you second element is a negative
Oh.
4/t?
Thank you so much. Yes. Negative. Is that the only mistake?
Yes.
Thank you so much. Okay, so then we'll do the 2 square and 2 squared plus negative 2 over t squared plus 1 over t square like that. Okay, so this looks bad. 2 square root, obviously it's going to be a perfect square. We're going to have 4 plus 4 over t squared plus 1 over t to the 4th, like that. Which I have this funny feeling it's going to be 2 square root of a perfect square. What's the perfect square?
2 plus 1 over t squared.
Good. So squared. And again, technically we use, let's just always be good. Put absolute values down before we get rid of them. So we have absolute value of 2 plus 1 over t squared. Like that. Yeah, and I hate to say it, but I'm going to get a common denominator. So this is going to be 2 times, I think it's going to be 2t squared plus 1, right? Over t squared. Like that. Now, remember kappa is the magnitude of r prime cross r double prime over the magnitude of r prime to the 3rd. Like this. So I can just copy that numerator. And the magnitude of r prime, I think, is up here. And that'll be to the 3rd power. So it's horrible, but let's see. I've got a 2. I think there's a t to the 3rd. There's a 2t squared plus 1. I think that's all that's on top. And in the denominator, there's a 2t squared plus 1 to the 3rd. And then a t squared. Like that. So it looks like you're going to get 2t over 2t squared plus 1 squared. And I don't know if that's what we got before. I'm hoping that's what we got before. I'll check that real quick. Let me zip out and see. Right here. So this is the same as before. So, and I don't know if that doing the magnitude of t prime is really bad, by the way, because t is really hard to compute, and then t prime is hard to compute. And then the magnitude of t prime is hard to compute. So while this was bad, I think there's actually less computation here than doing what we did before. So while, you know, I call this a computational formula. If you hate cross products, maybe then you'll hate to compute it this way. And I'll just leave that to you. There's multiple formulas for things. Okay, and I'm going to pause here and see if there are questions. So many notes. This is humongous. All right, well, actually, I have 1, 2, 3. I have 3.5 pages left of notes. I don't know how many I've done so far. Probably 6 or 8. I don't know. All right. Just get to work. Okay, so this is as before. So the whole point is some of the formulas are easier in some contexts. You'll see a couple, as you see, we have a couple different formulas for kappa. And there are other, kappa is going to be related to acceleration soon. I should say centripetal acceleration. I should probably do a plane curve real quick. So we'll do plane curves like y equals f of x. Okay, what's the curvature? I don't remember. They used to cover this in Math 180 as an application of derivatives, but I don't think they cover that anymore. So we have to think of a way to describe curvature for a plane curve. Well, we just do this by parameterizing. So r of t, before I do that, I would say x is t and y is f of t. Okay, so then my r of t would just be x of t, y of t. So this will be t, f of t. And then I'm just going to use one of the formulas. So let's do r prime of t. Okay, so this will be 1 f prime of t, like that. And then the magnitude of r prime of t will be the square root of 1 squared plus f prime of t squared, like that. Okay. And then we have to do r prime cross r double prime. So, all right, so r double prime of t will be 0 f double prime of t, like that. And now the cross product, r prime cross r double prime. We're computing curvature. Okay, so now I have to do this. I'll just write f prime and leave the t out, 0. And then 0 f double prime 0 with the i's, j's, and k's. Like that. And because this curve lives in the plane, we know that both of these vectors live in the plane, r prime and r double prime. And therefore the cross product will be perpendicular to the plane and have only a k component. And you can kind of do the work in your head, but it's not hard to see that if you do the I component, you'll be doing this and you'll get 0 minus the j, minus the j component. And as I say before, you can see that the determinant is going to be 0 minus 0 there as well. So we can say j times 0. And then plus the k component, which will be the only component. So the k component goes this way, and you can see there's a 1 times f double prime minus 0. So it's just f times f double prime. Okay. I'll do f double prime of t. So if we wanted, we'd write this as a vector 0, 0, f double prime of t, like that. And then if we take the magnitude of r prime cross r double prime. In the end, it's because this points in the z direction, you're going to be squaring the z component and taking a square root, which, as I've said repeatedly, just does the absolute value. So this is just going to be absolute value of f double prime of t. Okay. And now I think we can compute kappa here. Kappa will be magnitude of r prime cross r double prime over magnitude of r prime to the third. So here, you're just going to have the absolute value of f double prime of t. Curvature, this should be enough to tell you curvature is always positive. I think I've said that, but it's taking magnitudes always with curvature, right? The magnitude of r prime cross r double prime over the magnitude. So it makes sense that you see absolute values in this formula. Okay, and then over, without the absolute value, this could go negative. So we're doing the square root up here to the third power. So I'm just going to write that to the 3/2. So I'll do 1 plus f prime of t squared. And then the square root of that to the third power will be to the 3/2, like that. Okay, so that's sort of a theorem too. Oh, right, this is a theorem. So for y equals f of x, kappa, you don't need to bring t into it. You can just say kappa is the magnitude, sorry, the absolute value of f double prime of x over 1 plus f prime of x squared to the 3/2 power. Okay, so that's just another formula. So let's do a quick example of that. Okay, let's do y equals y equals x squared at the point 0, 0. Okay. Okay, so x squared is obviously my f of x. Okay, so f prime of x is 2x. F double prime of x is 2. Okay, so kappa is the absolute value of f double prime, which is, well, I could put the formula in, I guess. I'll just copy the formula down. Yeah. So this will be just 2 over 1 plus f prime of x. So I'll just say 2x quantity squared, and that's to the 3/2. Okay. When x is 0, kappa would be 2 over 1 plus 0 squared to the 3/2, right? So that's just 2. So the curvature is 2 there. What's the curvature of a straight line? Well, it should be 0 because the on a straight line, the unit, a tangent vector never changes direction. And remember, kappa measures how fast the tangent vector changes direction. So, you know, if we had y equals mx plus b, then we can call that f of x. Then y double prime or f double prime of x will be 0. So kappa would be absolute value of f double prime of x over, and of course the numerator is 0. So lines have 0 curvature. Okay, any questions? Let's do another example. I think we should know the curvature of a circle. So let's do a circle of radius A. Actually, I want to use rho. So circle of radius rho. Okay, remember rho is the Greek r. So it would be r of t equals rho cos t rho sine t, like that. And how do we do this? Let's use the other formula this time. So r prime of t, I don't want to do any more cross products. So this will be negative rho sine t and then rho cos t. And the magnitude of r prime of t will be square root of rho square sine square t plus rho square cos square t, which is just the square root of rho square, which is the absolute value of rho, which is just rho, because rho is the radius of a circle. Okay, so I'll just add up here rho is greater than 0 because it doesn't make sense otherwise. And so the unit tangent vector t, so t would be r prime over the magnitude of r prime. So r prime was up above, negative rho sine t rho cos t. It's a unit vector, so we have to divide by rho, which is the length. And so this does look like something on the unit circle. It's negative sine t cos t. And it's clearly a unit vector because the magnitude would have a sine square plus a cosine square, and that's 1. Okay, so we can see that's a unit vector, but it's a unit tangent. Kappa, oh wait, we have to do the magnitude of that. So, oh my God, the magnitude of t prime. So let's do t prime. So this is easy. So we're going to do negative cos t, negative sine t. Like that. And so remember, kappa looks at how fast t changes direction. And you can measure how fast t changes direction by looking at t prime's magnitude. So magnitude of t prime looks pretty easy. This is a unit vector, so this is just going to square root of cos squared t plus sine squared t, which is 1. So kappa is the magnitude of t prime over the magnitude of r prime. That was the first computational formula that we came up with. Okay, and so the magnitude t prime is just 1, and the magnitude of r prime is rho. Okay, so this is 1 over the radius of the circle. Okay, so the curvature of a circle is 1 divided by the radius. So we can see as the radius goes to 0, the curvature goes to infinity. And I want to go ahead and call it 1 over rho, just because the rho is going to have special significance. Okay, so as rho goes to 0, we see kappa goes to infinity. So it's sort of like the curvature of a point, because right, a circle becomes a point when the radius goes to 0. And so it's just becoming a really sharp turn, and effectively when it becomes a point, then the curvature is infinite. Okay, if you make the radius go to infinity, then the circle, the edge, the line that is a circle starts looking more and more like a line. So as the radius goes to infinity, the curvature goes to 0, and it becomes the circle becomes a straight line. Okay, sorta. So if you think back, we want to go ahead and define the radius of curvature. Rho to be 1 over kappa. Okay, this is the radius of what's called the oscillating circle. Now, this is a weird word, oscillating with 1 L. It's not like an AC circuit that oscillates. And I think I'm spelling it right. If you look up oscillating with an I, this is a tangent circle of the same radius. The word oscillating means kissing, so that's really sweet. It's the kissing circle. Just belongs on Valentine's Day, and it's not Valentine's Day. It's kind of sad. Okay, so this is a tangent circle with the same curvature as the curve. So let me draw a picture of what I mean there. So if I have like a curve, I'm just going to do a parabola here. And then I'm going to put a circle in here. I'm trying to match the curvature. Okay, so this isn't right. So I'm going to shrink this down until the curvature looks the same as the parabola. Still not right, it's too big. That's getting very close there. It's not perfect. Let's see if I can move this dude around here. It's because it wants to snap these shapes, and I don't like the snapping sometimes. It makes me want to snap. Ooh, that's pretty good right there. Okay, so let's just go ahead and pretend like that is that the curvatures match there. And let's just say at this point, the curvature is kappa. Okay. And I'm gonna have to enlarge this a little, so forgive me while I while I enlarge it. It's just I want to be able to draw a row inside that for the radius. I don't know if it'll let me. I'm trying to enlarge it. Doesn't seem to want to let me. There we go. Beautiful. Okay, and so I'm going to set the center of the circle again. It's called oscillating circle. Okay, so there's the center. And then what I'm going to do is just draw a radius in here, and we'll call that distance rho. Like that. So that's rho. And okay, so, and then just labeling everything, we have oscillating circle. See, it started kissing the curve. It's the oscillating circle. It's super sweet. We'll just do a little heart here. We can think of love when we talk about the oscillating circle. I feel a little bit insecure right now. Let me just Google this. Oops, I spelled it wrong. No, it must be with an O. I'm spelling it wrong. It must be a U. I don't know. Osculating. There we go. It's a U. Let me share. So I'm sorry. I'm ashamed of myself. There's the word right there. Right there. Osculate. And look at humor. It's kiss down here. Look at it's humorous though. It's like I would like to osculate you. That's kind of, it sounds nasty though. So I'm not going to say that again. I'll go to jail if I say that again. You guys okay out there?
Yeah.
Yeah, I'm doing good.
I feel bad that I got that with the recording. I can't believe I said that. So now I'm going to go to jail. All right.
So funny.
I was talking to my wife. Okay.
Oh, there you go.
I could say that to my wife.
Fine if it's your wife.
I thought it was on mute. Okay. So that's oscillate. Let me go back here. This is taking forever to get through. I'm so sorry. All right, so let's spell it right. Okay, so that's a U. And it's crazy, but I actually see this word in sort of advanced math books, just in different contexts. So I was looking at, I do a lot of 3D printing, mostly to help my son out because he likes to make minis. So he and I are always printing stuff on his 3D printer. And I saw this word when we were working out a 3D model. They were talking about some sort of oscillating shape. It was bizarre. Anyway, so there it is, oscillating circle. So if you went back to that parabola, remember we did y equals x squared a minute ago. So let's do that real quick. And we did the curvature at the origin. I may have to zoom in on this. Okay, so this is it. I'm going to go ahead and try and put an oscillating circle in here. So just to do my best to squeeze one of those in there. Things don't look as symmetric as I'd like, so I'm going to try and straighten the symmetry out a bit. Oh, I see what's wrong. I have to snap that right like that. That's pretty good. Okay, so I think you remember that this is y equals x squared. Let me get a little thinner here. I guess that's okay. So y equals x squared. At 0, the kappa was 2. At x equals 0. Okay, and that means so what I want to do is I'm going to say right there is the center of the oscillating circle, and that's a circle of radius 1/2. Okay, so this again is another picture I think I need to enlarge. So I'm going to try, pardon me. Well, it went up and then it shrunk again. Hey. Okay, so I'll just do this. I'm going to put a row there. Okay, so row is 1/2. Okay. And I think you might see a homework problem or two where they ask for the equation. So that's the oscillating circle. Okay, that would be well, there's no shift in x, so x squared plus it would be y minus 1/2 square equals the radius square, which would be 1/4, right? Okay. And there's probably, what time is it? 8:30. I got 5 minutes. Let me go ahead and put a couple definitions down. I'm going to have to do, this is not done, but I want to go ahead and give you enough where you can probably wrap up and do your homework on this if you want. I don't think I want to say much more about curvature, but there's the unit normal. Just to keep one thing in mind. I'm going to draw 2 tangent vectors and show you what direction the difference has to point. So how am I going to do this? These kind of have to be close together. So let me start over on this. I need 2 tangents that are real close together, and I think I need my turn to be pretty sharp. Okay, so what I'm going to do is I'm going to put 2 unit tangents just like this, real close together. Okay, one's going to point this way, and the other is going to point this way. So this is 2 tangent vectors. We could call that T of T. And this guy is going to be, this one down here is going to be T of T plus H. Okay, we're going to be looking at the derivative of T. Okay, we already know that it's perpendicular to T, but pointing this way between those is going to be T of T plus H minus T of T. Okay, which I'll also draw over here. Okay, that guy there is also T of T plus H minus T of T. Okay, and what you need to get from that picture is that that always points into the term. So note that T of T plus H minus t of t always points into the turn, to a turn. Into a curve, I'll say. Okay, so t prime of t, which is the limit as h goes to 0 of t plus h minus t of t over h points into the term. But also recall that t prime of t is perpendicular to the unit tangent. So that's a unit like this. Okay, so define in of t to be t prime over the of t over the magnitude of t prime of t. Okay. This is a unit normal that points into the turn and is perpendicular to t. Okay, so just before, we're not going to have a chance to compute this, obviously. I'll do this next time with you guys, okay, on Wednesday. But just a real quick picture here. We have the unit tangent this way. We have the unit normal this way. Unit normal will be important for determining acceleration. That gets a hat, not a barb. Acceleration is going to have a normal component. Okay, how are we doing for time? 8:36. There's another one. I'll define this one next time. There's a unit binormal. Is perpendicular to t and n. Okay, the unit binormal is super easy. It's just t cross n. Well, it's easy as long as you don't mind cross products. Okay, and you don't need, that turns out to be a unit vector naturally, so you don't have to divide by its magnitude. All right, that's enough punishment, but I do think that'll get you through that next section. Again, that was 13.3. Very big load of work. I think 13.4 is easy by comparison. So we'll do that quickly, and then we'll probably start chapter 14 next time, and then we'll also talk about your exam, which is next Monday. All right, I'll see you guys. Take care.
Thank you, Professor.
Have a good
Bye,
day, Professor.
everybody.
Thank you. Bye.
See you.
All right, so again, referring to this example we've been using, all of these are computations that we've done so far in this lesson, and we're going to compute this unit normal. Just remembering that any vector function that has a constant length will always be perpendicular to its derivative. Okay, so t is a unit tangent with constant length, T prime will therefore be perpendicular to it. So the unit normal just needs a vector that points in the direction of T prime with unit length. So we divide the length out and that gives the unit normal. So let's go ahead and do that real quick. Oops. So this is T prime over the magnitude of T prime. Okay, so here, we'll take this first one. Paste it down here and divide by the other one. Like that. Okay, and I think we're gonna have some cancellation. Looks like the twos cancel, but I'll still have a minus sign. So I think I'll hang on to that minus sign out front just for a minute. So you're gonna have a 2t, a 2t square minus 1, and a negative 2t. I don't like that minus sign, so we'll get rid of it in a second. So that'll be over just 2t squared plus 1. Okay, and so I'm going to go ahead and run that negative through. So I'll get a negative 2t and then a 1 minus 2t squared. And then a positive 2t. And I think that'll be easier to deal with in that form. Okay, any questions? So unit normal is done. You can distribute that through if you like, but you know, it's not necessary. Okay, and then the last one is the unit binormal. So I'm going to do my best and give you a picture of this. So the unit binormal is B, and it's a hat. So this is again unit binormal. Okay, this is T cross N. Okay, the magnitude, I'm saying it's a unit. Okay, to show that it's a unit, I'll go ahead and give you the magnitude. So the magnitude of this vector would be the magnitude of T cross N. Okay, and this vector will be, well, the magnitude will be equal to the magnitude of T times the magnitude of N times, is it a sine or a cosine?
Sine
Of what angle?
of the angle between T and N.
Which, and yes, and so.
So it'd be of 90 because they're perpendicular.
Exactly, so pi over 2, exactly right. So all these are 1, right? So all that is to say that B is a unit vector automatically. We don't have to scale it down to make it a unit vector. Hope that makes sense. So we just say this just in general. B is always a unit vector. Okay. We don't have to force that. So I guess we can run that through here. So let's go ahead and give it a go. So B is T cross N. Okay, so I'll just paste these down. So I don't like that. That minus sign is going to give me trouble. I can tell. Oh, no. T is different. It's up above. My bad. Okay, so T is this one. Cross that one. And the scalars can factor out of cross products. So that's what you really need to do here. You want to bring out this 1 over 2t squared plus 1, and that's squared. So let's bring out a 1 over 2t squared plus 1 square like that. And then we're just doing the cross product of the two vectors. Okay, so I'll go ahead and make that determinant here with the ijk. So in the first row, you're going to have a 1, a 2t. This would be a little bit messier, and a 2t square. Second row, you're going to have a negative 2t, a 1 minus 2t squared, which I don't like, and a 2t. Okay, and then of course ijk up on top. So that's one of the uglier cross products we've done. Any questions? Okay, well, so we've got this 1 over 2t squared plus 1 squared, and then I'll just do big parenthesis and an I hat. So for the I hat, we're going to do this computation here. So that's going to be 4t squared minus 2t squared, and then a double negative minus 4t to the fourth. No, I think it becomes a plus, right? Yeah, plus 4t to the fourth, like that. I hope. 4t squared minus 2t squared plus 4t to the fourth. Looks good. Minus j hat. Okay. So now we go on the extremes. So that looks like 2t minus negative 4t to the third. Oops. So that's plus 4t to the third plus k hat. Okay, and so for k hat, we're going this way. So we're going to get 1 minus 2t squared. And then minus negative 4t squared. So that's plus 4t squared. Like that. All right, so let's see how quickly we can clean that up.
Professor,
Yep.
really quickly, can I ask how you got how you took out 1 over 2t squared plus 1
Right.
squared?
Right, so scalars can factor out of cross products. So one of those scalars is this one. It just came out. And the other scalar is this one. I just brought it out front.
But what happened to the numerators?
The numerators are here and here in the cross product.
Oh, I see it now.
Yeah, I'm just crossing the vectors and bringing the scalars out. You see how nice it is to not involve those scalars in the cross product?
Yeah, that makes it easier.
Yeah, so that if you can factor scalars out before you do cross products, you should.
Okay, thank you.
Okay. Okay, so let's see if this cleans up here. So I got this 4t squared minus 2t squared plus, so that's 2t squared plus 4t to the fourth. I think I can factor out a 2t squared. Actually, I'm just going to use the vector symbol brackets now. So I think I'm going to have a 2t squared times 2t squared plus 1, comma. The next one's going to be a negative, and I'm going to factor out a 2t. And there will be a 2t squared plus 1. The next one, we're just going to have a 1 times a 2t. Oh, wait a minute. I think there's a mistake. No, it's just 2t squared plus 1. No mistakes. It's a miracle. And obviously, you can factor that 2t squared plus 1 out. So you end up with just 2t squared, comma, negative 2t, comma, 1 over 2t squared plus 1, because 2t squared plus 1 factor cancels one of the scalar factors in the denominator.
Professor, how did you get the answer for the k hat?
Okay, so you're going back to this?
Yeah, and then the answer below it.
Well, I mean, it just simplifies, right? 4t squared minus 2t squared is 2t squared.
Okay, I got it. Now I got it. Sorry.
No worries. Anybody else? Okay, and so that's it. We've just beat this thing to death. I think the only thing I might do is just kind of draw a picture so you can sort of see what this whole thing's about. So I'm going to add a page up above there. So give me one sec. It's right there, I think. Okay, so all I want to do here is just kind of give you a sense of what this is constructing. So you've got this curve. And I guess I'll put, now let me think about this. I think I'm going to draw the frame, what they call the TNB frame first. So I think I'll have this be my tangent. This is going to be B. This is going to be T. And then N is supposed to be sort of perpendicular to both of those. Like that. Okay, when I need my curve to do, and I'm going to dump that one. I don't like it. So I probably won't like this either, but yeah, I don't like that. Let me move that around a little so that it gives a good tangent vector. That's pretty good right there. Okay, so and remember these are perpendicular to each other. So the N is perpendicular to the T. And of course, the B is perpendicular to the T as well, and to N. So that's hard to kind of draw, but that's what's going on here. Everything's perpendicular to everything else. And these basically become an IJK coordinate system that moves with the curve. Remember, these are this is what we call the TNB frame. It's basically a moving basically an I, J, K coordinate system. Meaning it moves in time. Because everything's a function of t, right? And that turns out to be a super powerful thing. So when you get into it, and this is more of a math major thing, but math majors spend a lot of time doing math, not just on curves like this, but on surfaces that are three-dimensional and even higher dimensional. And the best way of describing things relative to a curve or a surface like that is in terms of that coordinate system that moves to any point you need to move it to. And it's just really easy to describe things in terms of that. So for example, like if somebody asked me to find the center of the oscillating, let me give you a point right here. So that point is R of t. Okay. And so if somebody wanted the oscillating circle, it's with a U, right? I'll just give the center and keep it simple. Oops. And just to remind you what the oscillating circle is, I'm going to go back up here. The oscillating circle is a tangent circle right here. It's a tangent circle that has the same curvature as the curve. So you got some nice pictures of the oscillating circle. And it's sort of hard to figure out where the center of it is, but don't be surprised if it comes up on your homework. It's like, where's the center of the oscillating circle? And the notion of doing that in three-dimensional space is just terrifying if you think about it. With a curve that's kind of looping all over the place in space, and someone says, find the center of this circle that's tangent to the curve. And it's just really hard math. Unless you have the IJK frame, or sorry, the TNB frame, where you could say the oscillating circle, what you do is you go to the point R of t, oops, hang on. So for the center of the circle, you would go to the point R of t, okay? And from there, what direction should I go, T, N, or B? For the center of the oscillating circle, should I go in the direction of T, N, or B?
N.
N, so how far? Does anybody remember the radius of the oscillating circle? I think it's up here. So the radius of curvature is the radius of the oscillating circle. So remember, n is a unit vector. So you would go a distance of rho in the direction of n. So you would do rho of t times a scalar times the unit vector n of t. N gives the direction, rho gives the distance. And that gives that equation right there, or that expression gives the oscillating circle center at any moment in time. And you can see it's easiest to express it in the coordinate system T, N, and B that moves with the curve, rather than trying to describe the center in XYZ coordinates or IJK, which are static. It's better to let the coordinate system move if you're trying to describe things about the circle. Or sorry, about the curve. Any of the geometric ideas on the curve are easier to describe with a moving coordinate system. And this is just a super important idea for math majors that go into differential geometry and whatnot. And this is the topic we're studying right now is actually called differential geometry. And in differential geometry, they study like what they call tangent bundles, which are basically coordinate systems that are local to any point on a surface or a curve. I think I'm going to stop there, and I think this is good enough to get you guys to say we've covered that. So I'm going to go ahead and stop the recording now.